All right, good afternoon again. Well, first things first, let me just address some things that were said before and what we have on the agenda. First of all, I'm no longer a lecturer at UTech. I was that three or 4 years ago. Doesn't mean I still don't have the information that's required. Which is also one of the challenges with presenting this lecture, because the information that I'm going to draw on really comes from about 5 2-hour lectures, and to compress that into the time frame I was told, which was less than we have on the agenda, was a major task for me. So you have to excuse that the slides you're going to see seem quite basic, because I try to stay within the time. I might stray because I believe there's some information that is very relevant, but I just didn't see how time was going. But we see how it goes, and we press on. With regard to the agenda, I'm listed as a member of the Jamaican Institute of Architects. I was, at the time, I was involved with the building code, well, other than the last one, but presently more involved in planning and implementation side of things, and more the facility management. So having said that, and without further ado, let me just go into things. One thing you have to look for is that generally I'm not somebody who likes to speak quite long, so that is a good thing. But the thing is that the topic I'm speaking about is something I'm quite passionate about, so if I can put something in, I will. Okay, so the topic, energy efficiency in Jamaica's building code, and even though you don't have it on your agenda, I was told specifically to speak about the envelope, but I'm actually going from the history coming through to the envelope. If some of you don't understand what building envelope is, we'll get to that as we go along. Everybody can hear me? Oh, okay. I saw some blank stares, so I was wondering if nobody could hear. All right, so we start off with, get used to this thing. A background into our energy code, which is very relevant to what we're doing here now. Relevant in the sense that if we do pay attention to what took place before, what UE is trying to do at this instant is going to end up very much what we're going to see right here. And just the very first statement says it all. That buildings, well, I got the first statement, it actually comes off the Twitter post that was made by Build Better Jamaica. And it stated that by 2050, the buildings should all be net zero if we are to avoid the consequences of climate change. Now, that means that within 33 years, all our buildings need to be net zero. Now, the reality, particularly with regard to the energy code, as I say on the last part of the slide here, last part of the first bullet point, is that Jamaica is yet to have a mandatory energy efficiency building code after 34 years. So we have 33 years to reach net zero, to build all of that. And yet 34 years, we still do have a mandatory code. So basically every building that's built is, whether you apply the energy code or not, is totally left up to the architect and engineer, which is not a good position to be in. So that is our reality. And that is what's taken place so far. And what you see so far, there's a lot, as I was going through preparing, I saw a lot of similarities in what UE is doing now and what PCJ did at the onset of the energy efficiency building code. So this is just a warning of what could happen. The energy code really got started when PCJ headquarters was being designed. which was about 82, early 80s. The person who did the first guideline for it was the engineer, the US engineer, Fred Dublin, I believe was his name, or Dublin, who came out to the United States, and he did the first guideline and the first draft to the energy code. The code that is now in effect came about in '95, which was 22 years ago. At that stage, the goal was that all government buildings would be built to the code, and that it will be something that will be mandated. So 22 years later, we're yet to reach there. All right, so as I said, it began with, wrong way, right. Began with this building, PCJ headquarters, because that's when it was being designed. And it's really sad that we have to go back at a building that is this old to, as an example of what we should be doing now. But that's the reality of the situation. There are two slides I have of the PCJ building. I wanted to pay particularly notice the difference in elevations. We won't deal with it initially, but hopefully I can come back to these slides and I will see to highlight what is different in this building as against what is typically even presently going up. So here we have the west-facing elevation of PCJ building, and one of the reasons I want to come back to the PCJ building is that I know quite a bit of it. I didn't work on it. My uncle worked there at the time, and he fed me quite a bit of information on it. By the way, the former OUR head, Winston, here is the uncle I refer to. So this is where he was before he went to JPS and OUR. All right, so as I said, pay attention to the difference in elevation. So you can see the stark difference between one view and the other. This is a view facing south. As I said, I hope to come back to it, that I had mentioned why that is so. All right, so in terms of history, what took place is that we had the draft building code coming out in '95, what was thought to be the final draft of it. Then it was thought prudent to assess the code, and this was actually done before the final draft came out. There were modifications, even though it was called final, modifications that took place because of this. The assessment was based off a computer simulation of really 4 different types. The slides would only mention 2 because the information I had only gave me data for 2. Even though it mentioned the other 2. And the 2 we're looking on is office buildings, small office buildings, and large office buildings. So the first thing that was done is to really get the utility bills for typical buildings that could be classed as large and those that could be classed as small. So we see from the slide that 17 large buildings were looked at, and they found the average to be 23.8 kilowatt hours per square foot. Secondly, the average for the small office buildings, and here you have a larger number, 82, and these buildings came out at 20 kilowatt hours per square foot. I apologize for it being in Imperial, but that is what the data was done at the time. And well, give more time, probably I would have converted it. But there are 2 things I want to point out before I go any further. First of all, is that we're speaking about the energy efficiency building code, and a lot of times, especially designers, just want to pass the code. I don't want to just endorse passing the code, right? You can say as we go further, you can actually exceed it significantly and get benefits to it. So really, if you really want to be strategic, What you need to look at is what do you want from what you want from the building, and how are you going to achieve it. Just not thinking about passing the code, because you're going to see that really passing the code is some very simple measures can be done to pass the code. The second thing I want to point out is that you will notice that the smaller buildings seem to be more efficient than the larger buildings. Now, that should not be so. All right? But having been involved, I didn't actually do the computer simulations, but I spoke with the engineers who did it, because they came up with the models. They spoke with me about the models before they did, so I know what those models are. And the thing is that the smaller office buildings, well, first of all, the larger office buildings typically would have all 4 walls free. Okay, so you have, as you saw with the PCJ building, where you saw the south wall and the west wall being different in elevations, you're going to see from the next slide that the typical building you find, office building, doesn't make that distinction. And the next thing you're going to see is that with regard to small buildings, is that the small buildings tend to be grouped together. So essentially they're functioning as a larger building, even though they're modeled as a small building. Okay, so the actual model that was done for a small building had the east and west side, which happened to be the largest, the walls that give you the most heat load, or sorry, cooling load. Because Jamaica has no heat load. Those are the walls that, not so much the east wall, but particularly the west wall that you saw with the PCJ building. That one gives you the most cooling loads. That's the most energy that the air conditioner has to expend to keep the building cool comes from that phase. So when you join them up like a townhouse, it means that it becomes more efficient because of that arrangement. So typically, the small office building, if it is detached, it will not be more efficient than the large office building. Even not considering the envelope at all, but even considering even the things like air conditioning. Larger air conditions tend to be more efficient than a lot of smaller ones. All right? So having said that, to move on, but this is what they found, that is what exists now, and I'm sure we're not too far from that now. One thing I can say is that I have noticed a lot more buildings being built now with insulation on the roof, which is a good practice, because the roof tends to be it's worse than the west wall, let's put it that way. So when you put insulation there, you can only benefit from it. So I think we're a little better off at that stage, but I think the data that comes out of it, which mainly is what we're looking at, is quite relevant, which is, as I said, sad to say after almost 20 years, but nevertheless, let's push on. All right, so we're still on assessing the code. So far, they found out what the typical building, the reason they want to find out what the typical energy use is that they want to simulate that in a computer building, a computer model, that when they make changes, they will see what those changes will bring about in terms of consumption. So I already mentioned some of the things, the comparable models that came up in terms of a large building. That, as a matter of fact, that large building was square, and the smaller building was rectangular, but something like a townhouse, it wasn't detached. They modeled annual and peak electrical consumptions and divided them up into system loads. I'll speak about it shortly in the next bullet point. But just to point out here why they need to model both peak and annual loads. Because this is of importance, especially if you have to put up a building, is that the annual loads is basically going to tie in with what your bills are going to be when you add them up over the year. But the peak loads are how you size your equipment. So how large your AC equipment is depends on that peak load. So if you have a high peak load, it means your air conditioning system has to be bigger because it is designed to cope with the worst load, worst situation you can have. Okay, so that's where peak load comes in. How this affects net zero buildings, where you're actually creating energy. It means if you are using less energy, you have to create less energy to be used. Right? So that's the benefit of actually creating a energy efficiency building. All right, so that's the reason they did that. Now the findings. System loads from highest to lowest are organized as is shown, and this holds for both the large building and small building. The cooling plant was the largest, significantly larger than all the rest, I should mention. Lighting came next, fans, the equipment was the last thing in terms of energy conservation. And just to give you an idea of the magnitudes, I deliberately left off the magnitudes because, as I said, the models change and this would change the whole thing. But the order in which they come is particularly relevant. But the cooling plant used about 3 times the amount that you had for lighting. So it's significantly larger, which means that, and cooling is one of the things you shall say that the building envelope actually addresses directly. It can address lighting, and I'm going to touch on that also. So it can actually impact those two. With regard to the peak cooling loads, differences were noted, and I should mention it's not large differences, but nevertheless, differences were noted from the large office buildings and the small office buildings. The main difference is that the actual loads are different, and I'll show you as we go along with the next slide. Okay, here we have a picture of New Kingston. And what you see is that most of the buildings there are over 30 years anyhow, with the exception of a couple of them. Some of them had modifications over that time, but most of them were built before and they still have had no modification. So hence that's why I stated that the relevant, that study is still relevant today. And I have a blog and I'm just amazed. A lot of times what I like to do is to take things that are in print, read what they say, and look at today's reality and see, are they still relevant? And I'm surprised the amount of times that, particularly coming out of UWI, that things that were said that are still relevant today, sometimes up to 50 years later. And it's a sad statement on society, but it's, as I said, it's reality. All right, so this represents a picture of the large buildings. What you'll see is that typically there's no difference between the different orientation of those walls. So the peak cooling loads here, and again, from highest to lowest, is that ventilation was one of the highest. Solar came next, conduction, lighting, occupants, and equipment. When you go to the small, you'll notice that there's a switch between conduction and lighting. So that switches, and I shall explain why as we go along. So this is our aerial shot. Well, still can say New Kingston inside here. Same loads, but you notice ventilation is still first, solar is still second, but there's no what? Right, there's no a switch between lighting and conduction. I thought I left something out. But occupants come second to last, and equipment is last. I'm just reminding you that these are cooling loads. These are things that give off heat and have to be cooled by the air conditioners to keep them at the same temperature. So ventilation, what we're speaking about there is particularly to deal with humidity. And because we're human beings, we can't, our air has to be, we can't just deal with recirculated air. Hence why that becomes first. The possible reason for switching of conduction and lighting, again, as I said before, it's basically only 2 walls that these small buildings have that are offering any sort of conduction. So that might not be typical if it's a detached unit. All right, we're still on assessing the code because what we've had so far was basically what exists. So now we're looking at the energy efficiency and how that will be impacted by making changes and ultimately what changes were made. We shall see that. Now changes were made to the building to comply with code, and what we got was for the large office, we have reductions of energy use by 30%. And for the small building, a reduction of 36%. The engineers took it a bit further, and I should mention that the engineers here, it was done by a firm called Enotech. They're no longer in existence. But one of the things they did was to go a step further to show, is it possible to go beyond the code? And as I've been suggesting, is that we shouldn't just try to pass the code. We try to go beyond because we can actually benefit from it. There is a limit because there comes a time and a space where it's not cost efficient, let's put it that way. You're just spending too much money and not getting the effect. All right, with regard to the actually surpassing the code, what they found with large office buildings, you can actually reduce energy by 62%, and by the smaller buildings by 57%. So now you start to see the benefits of the large building based off of the energy effort. So hence these could have significant impact or can have significant impact if they are implemented. All right, now how does that influence our building envelope? And as I said before, what really is a building envelope anyway? All right, if we consider this a normal envelope, right? The normal envelope contains whatever you put in a letter or whatever. Essentially, that's what a building envelope is. It's basically the walls and the roof of a building. For this purpose, I think I prefer another term that is used by both architects and engineers. They refer to the same thing as a building skin. So the same function that the skin serves, which is to keep the human body at a constant temperature. It moderates between your environment, and that's the purpose of your building envelope. Right. So when we speak about walls and roof, we also, I don't want you to think that windows or skylights are separate. Those are also part and parcel of the envelope. What we can find in terms of looking at the building envelope now, in terms of the effect, is that it cannot affect the consumption of equipment, but this is about 7%, approximately 7% of the annual consumption, and only 9% of the peak electrical consumption. So hence, it can affect a major part of our energy use. And this depends on various things. Next bullet point. With regard to the cooling plant, we saw that ventilation was a major issue there. Well, let me stick to the bullet point before I move on that tangent. It cannot affect occupant loads. Occupant loads are like what we have here, people inside the buildings. As was mentioned before, the buildings are meant for the people. It's not the other way around. The other thing it can't affect is equipment load. How it affects ventilation load is that you will notice these days that most windows tend to be fixed, which means they cannot be opened, all right? When you have operable windows, you have more air coming through or cold air coming out of those joints. So that's the only way it really affects ventilation, but it's not a major influence of ventilation. The time is running out, so let me just move along. As I mentioned before, it can affect lighting, and the way it affects lighting by something called daylighting. I just mentioned here as using daylight, but if you consider it, we have daylight. When it's mentioned, solar is mentioned for its energy, but a lot of people don't see it also. Well, we know it, but we just don't say is that it's also a light source. So if you use that light source, that's how you influence lighting. If particularly designers, for example, will look at a building like the Freedom Towers that was built in New York, and they say mainly glass building, and maybe they want to put up something similar, even not knowing that the Freedom Tower uses daylighting. A lot of those offices that are along that glass wall, those lights are automatically shut off when the lighting conditions permit, and they're turned on when it doesn't. So it is actually using daylighting to use so much glass. I wouldn't recommend you use a lot of glass in Jamaica. One rule of thumb with regard to glass, by the way, is that the more glass you have in a building is the more heat you're bringing into the building, even if you're using daylighting. That's the reality of our tropical climate. Right, so the less glass you can have, less glaze space, the better off you are. Now, what we're going to see, as I mentioned before, is that it's very simple to meet these codes. All right, so how did the large building, for example, cut down their energy bill by 30%? Right, it's very simple, 3 simple measures that were done. One, as I mentioned before, the roof is a major source of heat gain. It's insulated, and in the case of these buildings, it only took 1 inch of insulation. Typically, buildings now put 2 inches are put on them. And for those of you who know the insulation value, it was on a R4 insulation that was put on that roof to pass the code. Before I go a bit any further, let me just mention something that this is just goes to show the amount of effort that was put into the code, and that we have we really squandered it. Is that the computer something else I forgot, but anyway, the computer's programs that could be used to find out if you pass or don't pass was the computer codes were actually distributed to the people who came to the workshop like this. So it was something that people had in front of them. They got the climatic data so they could do it themselves. So this was the effort that went into it, and you played a part in that. This study that was shown here, the climatic data actually came from the Mona campus, because it was the only data that was in the format that was needed for the computer programs. Later on, as we reached the workshops, the Kingston data came out and it was distributed. So let me push on. The next thing that was done is special glazing and shading was used for the windows. As I mentioned before, you want to keep your windows to a minimum. And if you have to go larger than for whatever reasons, you can shade them, or you can use special glass. When I talk about special glass, I talk about, I don't want to mention reflective glasses, because typically, I don't want to get into too much, but glasses like the NZEB building, for example, where you have the gold reflective glass. Gold glass, you can get them that doesn't have a tint. Gold glass is one of the most effective transmitters of light, while it's cutting down heat at the same time. So it allows more light to pass through than heat. So that's why it is more effective. All right, so things like that were used. And the third thing is that simply they found that you didn't need to use insulation on the walls. Simply painting walls a light color. Doesn't have to be white. If you remember the PCJ building, it was actually white, so it's very light. So that was the only thing they did for the wall, and this is what passed it in terms of the building envelope. They did other things otherwise, but this was all that it took for the envelope to pass. So it goes to show it's not a lot that's required. In conclusion, because I'm told that I brought out the time, the Bureau of Standards deadline for comment on a mandatory energy efficiency code ended last month, so I'm expecting that we'll soon be hearing when that energy efficiency code will come become mandatory. And this has, secondly, it is now adopting the 2009 International Building Code we saw earlier, where it was the 2018 code that is being adopted for the Caribbean, which is a good thing, because that's it. The last thing here is that the Regional Building Code, which is the one that is adopting the 2018 Energy Code, is being developed, and we just hope that with all this that is happening, that we'll be in a better stead for the next, well, heading towards 2050. One point I omitted is that the Energy Efficiency Building Code is renewed it's updated every 3 years. So even though we haven't looked at ours for quite a while, it means the next time we look at it, we're looking at, it has been gone through a number of updates, so we don't have to look too far, we can just update it from the latest one. All right, so thank you very much.